All right, guys. Sorry I couldn't be there today. I'll be at home with Millie, but I'll be available. All right. So just shoot me an email if you run into any questions, any issues, and I'll be back tomorrow. But we got a lot. We got a lot on our plate here. A lot of it is review. So today in class and yesterday in class are just basically a review of the first 2 days. So all of these assignments here, days 1, 2, 3, 4, self-assessments and portfolios are all based on solving systems of equations. All right, so we're going to get a ton of practice here. So what I wanted to do is just go through some of the completed notes that are already accessible to you on our Canvas page. Okay, if you go to our calendar, it's all there. But I just wanted to kind of walk you through a bit more. So I know that we left off right around here, if I remember correctly. So that's where we'll pick up. So basically these are just base sketches, right? So like, you know that this has a y-intercept of 5, this line, and if that line has a y-intercept of 5, it's going to cross right around there at 5, right? This guy right here, you can kind of play around with and get a vertex for by using negative b over 2a. And you can go negative, well, it's just 0 over 2 times 2. So you get an axis of symmetry of 0, and then when you plug it back in, and you get, let's see here. Sorry, change the transparency a little bit. Let me turn that back down. And you plug that back in, we're going to get 2. Sorry, hold on. We'll get 2 times 0 squared plus 1. Those just wipe out. Y is equal to 1. So basically what you just determined is the vertex is at 0, 1. And that is this guy right here, which also happens to be the y-intercept, right? And it opens up. So this is just a basic sketch. And what this does for you is it helps you determine, okay, well, I know that I'm looking for 2 solutions. So it's just a good skill to have there. Now down below, what was done is the quadratic is set equal to the linear. You get everything on one side equal to 0. Now, once that's done, I think most of you would go to the quadratic formula from this point, right? And just say a is equal to 2, b is equal to 2, and c is equal to negative 4. And if you do quadratic formula with that correctly, you're going to get 2 x values of negative 2 and 1. Now, this is cool. Miss Danielson did a different way. From here to here, she factored out a 2. You can pull a 2 out here, a 2 out here, and you can pull a 2 out of negative 4. And ultimately, what you end up working with is this part right here. And you can throw that into a diamond, and you get the same solutions, negative 2 and 1. So it's just a different method that's shown there. But again, not comfortable with that. Just a quadratic formula with the a, b, and the c values here. Now what was done next is the x values were plugged back in, because in systems we're not done, right? In systems, different from the solving season, we now need to plug the x's back in to get the y's. So when that's done, you get a y value of 9 that goes with 2, or negative 2, and a y value of 3 that goes with 1. All right, let's take a look at this guy. So same kind of method here. X out. You know that this is just negative x plus 0, right? So it's going to go through the origin at 0, and it's going to be just downward sloping. This guy, if you were to go negative b over 2a and just determine the vertex, you'd go negative 1 over 2 times 1, and you'd get an axis of symmetry at 0.5, negative 0.5. And then when you plug that back in to the quadratic of negative 0.5 squared plus 0.5, sorry, I guess that's a negative. Let me just double check here, negative b over 2, yep. And then add 3. What you end up with is 0.25 minus 0.5 plus 3. So that's a negative 0.25 plus 3. So that gives you 2.75. So you know that your vertex is going to be at negative 0.5, comma 2.75. And that's going to be right about here. And again, all this does for you is you just create a quick sketch. Now you know from this sketch that we're going to be looking at complex solutions, right? And you can see here that when you set them equal, and you get everything on one side equal to 0, and do the quadratic formula with an a of 1, a b of 2, and a c of 3, you get solutions of -1 plus or minus I root 2. Note here, there's no need to go further by plugging that back in to find a y value that goes with it. That would get really ugly. That is right there good enough. You stop there. You have complex solutions of -1 plus I root 2 and -1 minus I root 2. Okay, down here, it's honestly more of the same. What's cool about the purple problem on the left is that when you set them equal, okay, to each other, and you get them on one side equal to 0, you can use ZPP. It's factorable. If you don't pick that up right away, then you can just do quadratic formula with an a of 1, a b of 5, and a c of -6. And when you do that, you're going to get these same two x values. Okay. Now, once you're done with that, you have to plug it back in. But the nice thing is, y is always going to equal 6. So that goes with the x value of 1. And it also goes with the x value of -6. So you have your two solutions, -6, 6, and 1, 6. The second one in the blue, as you can see through the worked solutions, these are irrational solutions, right? It's not going to be factorable. You can try the diamond and get them, set them equal and get them all on one side equal to 0. You can try to go diamond method, but you're going to see it's not going to work. So with an a of 1, a b of 2, and a c of -12, you can see as you work through the quadratic formula, you're going to get to root 52, and you're going to have to simplify that thing to become a pair of 2's. 13 stays under since it doesn't pair with anything, and it goes back in here. You can see that root 52 is simplified. Now -2 over 2 simplifies to -1, and this 2 over 2 just cancel, and you're left with root 13. So what we have is we have -1 plus root 13 and -1 minus root 13. That's not going to help us when we're trying to estimate y values, though. So what we do is we round this to 2.61, and we round this to -4.61 using a calculator. And then when you plug those back in respectively, you're able to get the y value that goes with each of those x's. Okay? You can always double check your work, always, by just plugging them into Desmos and seeing where they cross and getting solutions, or confirming your solutions, so you can do that on your own. Okay, wrapping this thing up. This will be the last one for today's notes before you go get to work on some review, is we have Pool A and Pool B. Okay, so Pool A is steadily increasing, so maybe doing something like that. Okay. Pool B rose at first and then began to decrease. Okay, this looks a lot like a linear and a quadratic to me. Now what was done here is it was just solved for algebraically. Okay, so get everything on one side equal to 0. What Miss Danielson did here in her worked out notes is she divided by -1. Okay, now what she did that for was when you divide by -1, it changes each of these a, b, and c values, because 0 divided by -1 is always going to be 0. But when you divide this whole side by -1, all of the signs just change. And that allowed her to then go on and use ZPP. She likes to use ZPP. If you don't want to mess with that, you can just throw it in the quadratic formula, and you have a is equal to -1, b is equal to 11, c is equal to 60. And with those values of a, b, and c, you're going to get these same two x values of 15 and -4. Okay? So that's still not like the real worldy application, right? We're going to apply what 15 and -4 mean shortly. Well, we can actually. I mean, it says since opening day, the number of days x. We know that Pool A and Pool B are going to have the same attendance on day 15 and on day -4. So we'll continue that in a second. Now, number 1 is just asking what's the maximum attendance for Pool B. If that's modeled by a quadratic, this is the max, right? And it's going to be concave down, and we know that because Pool B has a negative a value. Just like we did earlier, you can go negative b over 2a, and you get an axis of symmetry at 19.5. Okay? But then you have to take that and you have to plug it back in to solve for the y value. Now, you can't have 444 people. sorry, 444.25 people. You either have 444 people or you have 445 people. There's no in between. So we say it's about 444 people. And they hit their max. We can say their max occurs between the 19th and 20th days at about 444 people. Okay, it's just an approximation. Okay, now jumping down to 2, it wants to know who had the higher attendance on day 20. We know that day 20 is X, right? If we go back up here, it says X is the number of days since opening. So day 20 is just going to be X equals 20. Plug that into the linear, you get that pool A had 564 people present on day 20. Plug that into the quadratic right here, okay, into both spots, and you simplify from there. You get that, well, we already know this, about 444 people. So pool A has the higher attendance on day 20. Now, last thing, number 3. On what days were the attendance the same for each pool? We know without context that this quadratic and this line, they intersect at 15 and -4. Okay, but when we're talking about context, right, the attendance is the same on the -4th and the 15th days. -4 doesn't make sense. We can't go back in time. But we can say that on day 15, pool A and pool B had the same attendance. Okay, so that's on day 15 right here. Okay, what exactly it was, we don't care, but we just know that it had the same. Okay, they had the same attendance on day 15. We could plug it in and find out, but it doesn't matter. Now after day 15, the line will always have more because the quadratic is working its way down. Before day 15, the quadratic had more and the linear had less. Once day 15 hits, they have the same, and after that, it looks like the linear takes over as the more popular pool. Okay, so down here, you can just add whatever notes you need. Maybe you jot down some questions that you want to ask. I'll be back tomorrow. And again, email me with any questions at all. I'll be here to help you guys. And we'll pick up on the day 5 notes when I get back. Okay? All right, guys, I hope that helps.